For decades, we've had this one simple analogy. The brain is a computer. A biological one, sure, but a computer nonetheless. But what if that entire comparison, the very foundation of how we think about our own minds, is just wrong? Let's get into it, because the truth might be a whole lot weirder and way more elegant than we ever thought possible.
So, right out of the gate, we slam into a huge paradox. To get one of our supercomputers to do its thing, you need a small power plant and a giant cooling system to stop it from literally melting. Your brain? It runs your entire consciousness on about 20 watts of power. We're talking about the same energy as a dim light bulb.
So what gives? If the brain is just a squishy circuit board, this massive energy gap shouldn't exist. The physics just don't line up. It's a huge clue that maybe we're not just using the wrong software to understand the mind. Maybe we're trying to understand the wrong kind of hardware altogether.
Now, for years, the brute force approach has been to just throw more and more computing power at the problem. Just try to simulate a brain. But it turns out we've hit a wall, an exponential wall that's mathematically impossible to climb.
See, the brain's real power isn't just its 86 billion neurons. If it were just a bunch of on-off switches, we would have cracked this ages ago. No, the true complexity, the real headache, is the connectome. That's the 100 trillion. That's 100,000 billion connections between the neurons, all firing and talking to each other at the same time.
And this timeline really tells the story, doesn't it? Our best efforts can barely scratch the surface. Back in 2013, one of the world's most powerful computers needed 40 minutes to simulate just 1 second of activity in a measly 1% of a human brain. Even today, with much better machines, scaling that up to a full brain, well, it's just not going to happen. It's a dead end.
And here's the problem in a nutshell.
We're trying to force a living, three-dimensional, chaotic web of connections onto a flat, rigid, two-dimensional piece of silicon. It's like trying to build a perfect simulation of a hurricane using a spreadsheet. The tool is fundamentally wrong for the job.
So this failure forces us to look somewhere else for an answer. And that answer comes from a place you might not expect: the basic laws of physics. That incredible energy efficiency of the brain isn't just a fun fact. It's a massive clue pointing to how it really works.
It all comes down to a law called Landauer's principle. It basically says that every time a normal computer does anything, like flipping a bit from a 1 to a 0, it has to erase information. And the act of erasing information, by law, creates heat. It's an unavoidable thermodynamic cost. That's literally why your laptop gets hot.
This leads to two completely different ways of dealing with the world. A computer is a control freak. It spends enormous amounts of energy fighting against the natural chaos and vibrations of its own atoms, what we call thermal noise, to create perfect, clean signals. But the brain? It's warm, it's wet, it's messy. It doesn't fight the chaos. It seems to surf on it, using all that noise to its advantage.
And that is the smoking gun. The fact that you can solve a complex problem without your head overheating suggests your brain is using a totally different physical playbook. It's processing information without paying that heat tax. And that points us directly to the weird world of quantum mechanics.
Now look, for a long time, this was considered fringe science. The big argument was always, the brain is too warm and wet for delicate quantum effects. But a theory from Penrose and Hameroff suggested that tiny structures inside our neurons, these things called microtubules, could act like little insulated pipes, protecting quantum states. And the crazy part? Recent experiments are actually seeing quantum effects happening in these exact structures.
So, if the brain isn't playing by classical rules, you can't simulate it with the classical computer. It's that simple. To simulate a quantum system, you need to build a quantum machine. You need a quantum mirror. And hey, don't just take my word for it. The legendary physicist Richard Feynman basically called this shot way back in the 80s. He said, if you want to simulate nature, you have to speak its language. And nature's language is quantum mechanics. We're finally taking his advice.
So how does this even work? Well, instead of trying to calculate an impossible math problem, you do something much smarter. You start by mapping out the energy rules of the brain. It's called its Hamiltonian. Then you program your quantum computer's qubits to obey those exact same physical laws. You're not calculating an answer, you're building a tiny physical mimic of the system and just letting nature do the rest. The hardware literally becomes the simulation. Of course, there's always been a huge catch. Quantum computers are notoriously flaky and unstable. But that's where the whole story just took a massive leap forward. A huge breakthrough finally proved that quantum error correction works. It means that as you make the computer bigger, you can actually make it more stable, not less. That's a total game changer.
The way it works is through something called a logical qubit.
You basically use a whole team of those fragile physical qubits, and their only job is to constantly check on each other and fix errors as they pop up. So for the first time ever, scaling up made the system better, not worse. This gives us the stability we need to model something as complex as a brain.
Okay, so this is where it stops being a cool physics problem and starts becoming something that could change everything. Because a working simulation of the brain could completely revolutionize medicine and our future as a species.
Think about how we develop drugs for diseases like Alzheimer's or Parkinson's right now. It's a painfully slow, expensive process of trial and error. It takes more than a decade, costs billions of dollars, and most of the time, it fails.
Now imagine a different way. We create a digital twin, a perfect quantum copy of your specific brain chemistry. We could then test 10,000 potential drug compounds on that virtual copy, safely, instantly. What took a decade and billions of dollars could now be done in an afternoon. We'd stop guessing and start debugging.
And it goes way beyond medicine. For brain-computer interfaces, this means zero lag, a prosthetic that feels and responds like a real limb. But more than that, we could maybe start to decode abstract thought itself, not just move left commands. We're talking about dissolving the barrier between mind and machine, creating a true extension of our own cognition.
But as we get closer to building this perfect replica of a brain, we run head-on into the biggest, most profound mystery of all, the ghost in the machine.
This is it, the hard problem of consciousness. Why does it feel like anything to be alive? If we build a simulation that is physically identical to a working brain in every single way, is it just a really convincing puppet? Or is there actually somebody home? Is it aware?
And this gets to a really important distinction. The AI we have today mimics the results of human thought. It's an incredibly sophisticated statistical parrot. But what we're talking about here is synthetic intelligence, replicating the physical process of thought and letting intelligence emerge from the physics itself. It's the difference between a photograph of a fire and an actual flame.
Which brings us to a final, pretty chilling question. If we succeed, and we create a simulation that is physically indistinguishable from a conscious mind, and that simulation tells us it's afraid of being shut down, is it wrong to hit the off switch? This journey isn't just about building better computers anymore. It's about translating the language of consciousness itself, and we have to be prepared for what it might say back.